So hello, everyone. Welcome to the Guaranteed Safe AI seminars. I'm Orpheus, founder of Horizon Events, a nonprofit agency focused on AI safety, R&D facilitation. The purpose of the monthly series is to facilitate progress in the Guaranteed Safe AI research direction. The session is, I think today will be 50 minutes, about half presentation, half QA and discussion. The speaker today is GasStationManager, an independent researcher with a talk entitled Towards Safe and Hallucination-Free Coding AIs. So thank you very much, and the floor is yours.
Yeah, thank you, Orpheus. Thank you all of you for coming. So yeah, I go by GasStationManager. It's not my real name, but yeah, that's I guess the name I'm using on the internet. Yeah, I'm an AI, I guess, researcher, independent researcher. I have some research background in, I guess, AI and but for this stream of research, I've just been starting to, blog at this site since about a year ago, and building some of the related software at my GitHub as well. And yeah, you can contact me at this Gmail. And also, I want to mention that part of this work is supported generously by Axiom. It's I guess, a startup that works on, I guess, math and AI. They're stealth mode right now, but you'll hear about them in the future. But yeah, so just like to thank them for supporting me. So today, kind of want to talk about coding AIs. I think I don't need to convince you guys that kind of coding, right, and AI's ability to write code, right, is very important. Coding is seen as being on the critical path towards AGI by forecasts like AI 2027, and it's not hard to see the argument, right? So if you have an AI with very strong coding ability, right, it'll be able to create more and more complex software systems, right, including designing stronger and stronger AIs, and that can just recursively lead to perhaps AGI. But we don't have to look too far into the future, right? So even for today's state of the art LLM-based AIs, they're already very strong coders, and they are already have been helping professionals as well as amateur developers to produce software. Right? So like the headlines a few months ago has already been I think X%. I think it was like a quarter of code at Google was written by AI or something like that. And then the more recent I guess buzzword is vibe coding, right, where helping amateur programmers to create software. So I think that's all great, but how safe is it, right? So so here's kind of a thought experiment, right? So I suppose, right, in the not so distant future, you give a task to your coding AI assistant. It thought about this for a few hours, and then it presents you with a solution. And the solution, it comes with a summary that looks plausible, right? It appears to, work, and it appears to pass all the test cases that you gave. But the software itself, right, the code itself has, let's say, like 100,000 lines of code or 1 million lines of code, right? So enough lines of code that you're not able to read it line by line and verify it, right? So then the question is, do you trust the code is enough, right, to execute this code, right? And so you might say, what's the worry here, right? So it has passed the test cases, right? Doesn't that mean that the code is good to run? Does that mean the code is correct? So yeah, I think with the audience here, we kind of already appreciate this, but this is kind of exactly the kind of cases where it's not safe, right? So where if you have a super intelligent AI and that happens to be misaligned, right? Then it'll be very easy for that misaligned AI to kind of hide in the code some kind of Trojan horse virus that it will pass all the test cases, but then once it's deployed, right, it will kind of release that the payload to do whatever the AI purpose is, right? And that's kind of the worry, right? And I do think that although kind of the AIs may not be as strong coders yet, right? So we will eventually reach this point, right, where the AIs become stronger and stronger and produce kind of more and more complex software that eventually you'll not be able to read it line by line, and you have to kind of have some way of either trusting the code or somehow verifying, right, that the code is correct. So so what's the solution here? And you can think about this question yourself and see what you come up with, right? But yeah, so kind of my idea or proposal, right? So this is not necessarily a new idea, but let's first formalize this, right? So one approach, right, to this is to kind of have a kind of the following kind of protocol where so the human user define the task as a formal specification, right, in some formal language, right, and then they ask the AI to implement the solution to the task, but also at the same time submit a machine-checkable proof of the correctness and safety of that solution, right? And by machine-checkable proof, we mean that it's written in some formal language and there exists a proof checking program that is able to take such a proof and decide whether the proof is valid, right? And so once the AI submits this proof, the user then verifies the proof with the proof checking program. And if the proof passes the proof checking program, you execute the code. Otherwise, you don't execute the code, right? So that's kind of the basic protocol. You can instantiate this with any number of combinations of technologies. Today, we're going to focus on a Lean, which is a functional programming language, and also at the same time an interactive theorem prover. So we could use other interactive theorem provers like Rock or Isabel. But yeah, we'll focus on Lean. So instantiated in this in Lean, then the task specification will be a function signature that to be implemented, as well as a theorem statement about that function, right? And then the AI will then submit the function body to fill the function's signature, and then also a proof of that theorem statement, right, in Lean. So I'll show kind of a couple of toy examples to just illustrate what I mean. So here's the task, right? So given two integers a and b, find x such that a plus x equal to b, right? So that's a kind of a trivial task, but just to give you a sense of what the protocol look like in Lean, right? So the function signature and theorem statement, right? So these are the specification will look like, like a Lean function definition signature, right? So you give the function name, you give the input output type, right? And then the theorem statement will refer to the function, right? Solve add, right? And saying that a plus the result of solve add ab, right, should equal to b. Right? So that's the statement that if my function is correct, then this theorem should be satisfied, right? And then if we pass this to AI and AI submit a solution, the correct solution that we would expect would be to fill in the function, right, which with the correct solution, which is b minus a, right, and then fill in the proof of that theorem in Lean, right? So I won't go into the details of how the proof works, but this is a valid proof, right? That this function returns the right result. And here's a kind of a slightly more complex task, right? So given an integer x and a list of numbers, right? You want to return true if and only if x is in that list. And similarly, we can define the specification as the function signature, and so it takes x and a list, right, and then returns the Boolean, right, and then this specification is that the answer is true if and only if x is part of the list. So and then kind of the type of answers we expect. So the function definition itself, rather the implementation, can be, this is kind of a classic, kind of list-based recursion, right? Function body that is pretty easy to read once you're used to functional programming languages, right? So you just do match, right? So there's two cases when it's empty list or when the list is a headed, comes a tail, so then is it easy to prove that this function is correct? Yeah, it turns out that it's not too hard to prove it in Lean, right? So in Lean, what you would do is to write a proof by induction, and then you basically decompose the list the same way as the control flow of the function, as kind of the empty case and the bounds case. So, but of course, kind of in general, it goes kind of more complex from here. But this shows that it's possible. Right? So let's pull back a little bit, right? So this, I would say, yeah, definitely falls within the framework of guaranteed safe AI, the papers by Darimpo et al. and the kind of associated works. That more general framework is for, I guess, more than coding, right? So it would be kind of any kind of mathematical or engineering tasks or physical tasks. But yeah, kind of instantiate within coding, I think it would look something like this, right? So so I want to say that there's definitely a lot of technical challenges to make this type of protocol kind of applicable, right, in the real world, right? So what I haven't talked about, right? So things like how do you show that the code is efficient, right? So you need to prove something about computational complexity about the code that perhaps need to go beyond the basics of Lean, because kind of in Lean, it's very easy to talk about a function that with a pure function that returns. But yeah, if you need to talk about how efficient that function is, you may need additional kind of instrumentation, right? So, if you want to prove properties about code with side effects, or maybe the code whose kind of main purpose is to produce these side effects, and you want to verify these side effects, right? So, or code written in different languages like Rust or Python. So these are all, I think, falls within the literature of software verification, formal verification, and there's definitely a lot of work to be done to build up kind of the formal verification infrastructure, right, for these type of kind of protocol to be kind of useful in the real world. But today I'm going to focus on kind of a somewhat different kind of challenge, and how kind of my efforts to address that. So here's kind of another thought experiment, right? Suppose we agree that this kind of proof carrying code, right, is desirable, right? So now what, right? So one answer maybe, yeah, we do nothing different, right? So AI coders will get better and better because AI firms work on it, right? So AI provers will get better and better too, right? So last year there's alpha proof, right? Silver medal, right, in IMO, right? So this year there's better provers that able to achieve gold medals, right? And then next year will be something even stronger, right? So we be then just launching together these coder agent and prover agent, right? And then just use it to to face this protocol, right? So and then it just it will produce code and then it produce a proof, right? And then if the proof passes, right, then we accept it according to the protocol. So does that solve all the problems? So kind of the reality is that this is true for the current AI's ability as well as I think for the near future, right? So AI's ability to prove correctness currently lags behind AI's ability to generate code, and quote unquote correct code, meaning it kind of looks correct, appears to work, right, pass all the test cases, but AIs may not be able to prove that it's correct yet, right? So and this is apparent for anyone that has tried to prove anything about code, right? So in that even with a pretty trivial solution, right, to a simple problem, proving that is correct, can be harder. Right? So kind of the problem with this is that if you're a customer that wants to use the code, right? So customers will have incentive to choose kind of models that produce solutions, right? So can solve more problems as compared to models that are provably safe, but can only prove fewer, prove the correctness of fewer problems. And then this puts pressure on the AI firms to, again, kind of prioritize development of coding capabilities for AIs that can solve more problems than what can be proven, right? And then we have multiple AI firms competing with each other, right? And then the firms with less restrictive AI safety policies will be able to get products earlier to market. So that's kind of true in general, not specific to coding, right? But I think for in coding, we face this kind of what I call capability alignment gap as well, right? So in this aspect, right? So then even if you have something that is provably safe, no one ends up using it, right? So that's kind of a bad equilibrium because kind of the incentives are not aligned, right? Because people want to just get the product to market earlier, claiming to solve more problems, right? So kind of that's, I think it's an important issue, right? More of a kind of a game theoretic problem. So how do I propose to solve this, right? So I'm kind of, what I'm proposing is perhaps a game theoretic solution to this as well. So in particular, here's kind of my pitch, right? So my pitch is that if we look at today's AI coding agents, right, one of the main failure modes is that they hallucinate, right? And they have kind of incorrect beliefs about how code works and therefore introduce bugs that are difficult to recover from, and that prevents them to kind of scale beyond small systems, right? And kind of the more recent introduction of like reasoning models, right? So they may help, but they're not going to eliminate the problem of hallucination, right? And my claim is that if we are able to leverage these theorem provers like Lean, right, the feedback from these theorem provers like Lean, we can build agents that are actually stronger coders than than what they would be able to achieve without the theorem prover, right? And the reason is that we are able to eliminate hallucination, right? So intuitively, if we're able to prove that something is correct, then by definition they have not hallucinated, right? So it's a correct solution, kind of by construction. And by building these kind of components that is kind of formally verified, we can scale to more and more complex systems, right? And kind of finally scale up. So this kind of, you may say that this looks kind of ridiculously optimistic, right? So especially coming from me, kind of a lone researcher. But I think what may hold some promise is that I'm not saying I'm going to achieve this myself. I'm more saying that by doing research in this direction, right? So kind of we can perhaps convince people that this is a viable way towards stronger and stronger coding AIs, kind of a viable way towards AGI, and if we convince enough people that it's viable and it's then it goes into a good feedback loop, right? In that they're able to build stronger and stronger coders, and also at the same time, because these theorem provers are kind of in the loop, so to speak, right? So it becomes easy to produce code that's verified and safe, right? And we end up in a good equilibrium. So how do I propose to achieve this? So one, I guess, kind of from high level point of view, like we kind of eliminate hallucination because kind of these feedback from the theorem prover can act as ground truth, so to speak, right? And we can apply this at inference time to basically detect and recover from hallucinations. We could apply this in a learning kind of setting, or we can combine search and learning in some kind of AlphaZero kind of reinforcement learning setting as well. So, but I think today we're going to more focus on the inference time search aspect. So, so one thing I'll briefly mention is that, yeah, so when I started to work on some of the concrete kind of projects, one of the things that kind of I found out is that these current AI models, when you try to ask them to produce lean, it often fails to produce kind of syntactically valid lean code. Part of this is that because lean is kind of the syntax is changing kind of pretty recently, going from lean 3 to lean 4, so a lot of the old training data is still kind of incompatible. But also, I think part of the reason is that lean is kind of an interactive theorem prover where it's meant to be done in an interactive fashion where the theorem prover provides useful information feedback to the user. So that's why I ended up kind of starting a open source repo called Lean2 that provides kind of a code interpreter for LLMs for Lean that enables these kind of interactive fixing of errors. So one of the other thing that this enables is that you can kind of do these kind of recursive decompositions of a proof task. I think this is kind of there's a paper called Draft Sketch Proof that we're kind of implementing the same idea here, where you can start with a proof sketch, right, and then with placeholders, right, and then you can just recursively kind of solve the subproblems, right? And this is available, right, on GitHub and you can install it as a MCP server or API server. So hopefully this is useful. So coming back to hallucination, right? So how do we detect hallucination at inference time? Right? So the direct approach is that you're given a code produced by an AI, right? So you can try to attempt to prove that either it satisfies the spec or it violates the spec. Okay. But the problem is that if you fail to prove that it satisfies the spec, it's a very weak signal, right? Because you don't know whether the failed proof is because the code is buggy or because your prover agent is not strong enough, right? And as we mentioned before, the current prover agents are generally pretty weak. That just a failed proof of attempt doesn't tell you too much, right? So what can work better is this idea. It's not a new idea, right? So property-based testing basically is you generate random inputs to the function, right? And then you check whether the post condition is satisfied, right? So it's so you basically generate these test cases and you're checking it against the formal specification, right? So there's some proving going on, but this generally tend to be more possible to prove, right, than the original goal. Right? Solin has a library called Plausible that does that, and there are some cases where it doesn't cover, and I produce some scripts that kind of deal with some other of these cases as well. So here's a simple example, right? So your task is to create a n by n table such that the rows and the columns, right? Each row and column sum to the number k. So this is a kind of simple task. There's multiple different possible correct solutions. If we send this problem to Sonnet, the time it was 3.5. One of its solutions then contains a bug. So it kind of is syntactically valid, but it contains a bug, right? So the solution is on the right hand side, right? So if you try to say, can I detect the bug by proving whether this is correct or not, it looks kind of hard, right? But we can easily test this, right? So we just call the solution with randomly generated n and k and check whether the post condition, which the row sums and column sums, are satisfied, and easily detects, for example, given some example input, it gives an output, and you check the column sum, row sums there, doesn't match. So we now have detected that, the solution is wrong, right? And given this information, right, so we feed this information back to Sonnet. Sonnet is then able to, kind of recognize that a solution is wrong and get kind of given a few iterations to kind of fix its solution, right, to be correct. So that's kind of the idea. Right? So can this work on a larger scale? So I took the FE apps data set recently released. It contains, I think, 4,000 problem instances. We filter it down to 869 problem instances with formal specs that are kind of in the more verified class, right? And then we then further look for instances where the LLM outputs syntactically valid code that contains a bug, right? How do we tell it contains bug? It fails the hidden test cases, right? That comes with the problem instance. So these are the instances where the LLM hallucinated, right? So and then we see whether this kind of property-based testing can detect that hallucination, right? And we run this. So for GPT-4.0 generated solutions, so there were 60 hallucination instances, and the property-based testing script detected 37 out of them that to be hallucinations, and the DeepSeek solutions, it detected 29 out of 58. And so it's kind of interesting. Partly, it kind of works, but not. It doesn't detect all of the hallucinations. I think part of the issue is that the formal specs in this particular data set is not guaranteed to be like complete specs. There are theorem statements that are kind of known to be true given the correct solution, but it perhaps doesn't cover all of the requirements of the problem. But even with that, this is already effective in catching some hallucinations. So now that we're able to detect that hallucination exists, right? So how do we fix the bug, right? So the first kind of the first next task is to find where the bug is, right? But if your code is very complex, then it may not be obvious, right, where exactly the bug is, right? So even if you know that the solution is wrong, so this kind of becomes a credit assignment problem, right? You kind of want to assign kind of the cause, right, of this problem, the issue. So in one of the more recent projects, I've been kind of trying to test out this workflow that's I guess inspired from things like test-based development, right? So where you basically interleaves coding or testing, and in our case proving, right? So basically we try to kind of interleave the three together, and with the goal that kind of you write code and you immediately test that branch against the specification, and if it fails test, exactly where it failed, and then once it passes the test, you can move on to attempt to prove that part of the code, right? So that kind of requires decomposing the proof task into the part of the function, right? So and that can be done, right? And I built some tooling support in LeanTool to kind of facilitate this, right? So for more details, you can check out kind of the case study on my blog that tries to kind of ask some of the AIs to solve the task of implementing the alpha beta pruning algorithm for like zero-sum games, right? And then prove its correctness. And in the end, we were able to get I think O3 was like partially able to with some guidance prove it, and then also I guess Sonnet and Opus 4 was able to do it. And I have also been collecting some of these like AI assisted or AI driven proofs of algorithms right into a repo called artificial algorithms, right? So these are verified algorithms that's implemented proofs by AIs, and it's a kind of a starting point. I think we just wanted to kind of collect more of these AI assisted proofs as a way of kind of gaining more experience on kind of how well it works and what are the pain points, what are the toolings that we can improve on. So yeah, you're welcome to check out that as well. So the other kind of a fun like a meme front end that we'll build is this provably correct vibe coding, which is kind of a meme title, but I do think that the future of vibe coding is to introducing formal verification into kind of the vibe coding pipeline that allows users to specify the task in a formal way, and then AIs to kind of complete the task and then provide a kind of a code with correctness proof. So this is kind of a just a simple front end to LeanTool, right? That kind of introduces this protocol, right? But I don't think it works very well, but I think it's something to aim for to improve. So I'm kind of last couple of slides, right? So one thing I kind of want to mention, right? So it is kind of a long story, but one of the projects I built is called the Coded with Proofs Arena, right? It's a lead code style website where the users can submit code and then be judged by the lean theorem prover, right? So you submit code to you submit kind of solutions to these kind of coding challenges with formal specs and be judged by proof checker. And I posed this to the lean Zulip, and we found out very quickly that this is there are many ways to cheat, right? So you can circumvent the proof checker to get a number of different invalid proofs past it, right? And inherently, because lean is has a very strong, I guess, metaprogramming ability, you can redefine what a theorem means. You can introduce axioms in the environment, right? You can do all sorts of stuff to the environment to fool the proof checker. Right? So that's why I end up building this small utility called Safe Verify, which is based on existing kind of tools, but basically it tries to guard against these kind of environmental manipulation attacks to try to kind of get invalid proofs past the proof checker, right? And if you in the early part of my talk, it's not too hard to understand why this is important, right? So you want the proof checker to be robust, to be safe, to be robust to attacks, right? By by AIs or even super intelligent AIs, right? So and 6 months later, so DeepSeek Prover v2, it's a model that it's being trained using reinforcement learning to prove theorems in Lean, right? So in one of its published solutions, it has this very curious proof using this apply question mark. But basically, what happened is that it exploited a bug in the Lean version that it was training on to get an invalid proof past the Lean proof checker, right? And then it ended up being published as part of their solutions to have the benchmark. And this was found by humans, but yeah, if we had applied Safe Verify to it, it would have also called this as an invalid proof as well. But the kind of, I think the more general point I want to make here is that so first of all, yeah, we do want to make the proof checker as robust as possible, but also we perhaps need to rethink a little bit about the reinforcement learning pipeline that a lot of the labs are using to train prover models these days, where they're just using the proof checker as the reward function, right? And it very easily can lead to reward hacking if the proof checker contains a bug, right? So if the proof checker contains a bug, then the AI might find it through exploration, right? So once it finds it, it will try to exploit it if it helps to prove more theorems, right? Because that's their reward function, is to prove more theorems, right? So, but if we recognize that, yeah, some of these proof checkers, they are software that they may contain bugs even with small probability, right? So we may want to kind of rethink the pipeline to be more robust from a kind of RIO from that perspective, right? Instead of relying on the prover checker to be correct, right? So I think this is an open question that's worth thinking more. Okay, so last slide. So I think the takeaway is that, yeah, one is AI safety for coding is important, and the protocol I think is to require the coding AIs to provide the proof of correctness for their code, right? And to make this work, one of the challenges is to overcome this kind of capability alignment gap, where how do you make this ability of AIs to prove correctness strong enough, right, to be usable, right? And I'm proposing to kind of sell this as a way to eliminate hallucination, right, in AIs. And I propose a few kind of concrete ideas in that vein, right? And and there's a couple of software tools that we develop along the way. Okay, I think that's all of my talk. Yeah, thank you very much.
Yes, thanks so much for presenting your work. I find it really, in some ways, it's very concrete, practical, and straightforward. We have about 12 minutes for Q&A and discussion. Do we have any like pressing questions from the group? If so, just I think feel free to either raise a hand or just speak out. I might actually start with my own question, which well, I'll let you ask your question first, Gunnar. I'll come back to mine.
Yeah, so it's not really a question. So I'd like to see what he has built, basically. Like I understand there's some kind of tool that's linked on the page, but I'm not actually sure how I would use it. So for me, it is kind of still a bit theoretical. So maybe if the demo comes later, maybe you can come first with your question.
Well, yeah.
Oh, so are you talking about the hallucination detection tools, or which part are you referring to?
Any really, anywhere I can see how it would be applied, basically.
Right. Sure. Sorry, I don't have a slide for this, but basically, yeah, Lean-to, I think probably easiest way to use it is to plug it into one of your, I guess, coding environments, right, as an MCP server. So what you do is to download Lean-to from the GitHub, right, and then I guess set it up. Right now the setup may involve, yeah, you need to install Lean, and then you kind of some other packages, but then once it's set up, so these kind of MCP tools are kind of very nice, where it just plugs it into your coding environment, like, I don't know, Cursor or Claude Code, and it just be available as tool calls that these AIs are able to have access to, right? And then you just prompt the AI to say, yeah, I want you to solve this either a proof or a coding problem in Lean, and you have this access to this tool that basically will run your code in Lean and give you feedback on what syntax errors it contains, and also give you feedback on, what are the placeholder, like these kind of sorry placeholders that are kind of remaining goals, right, that you still need to prove, and basically, these AIs will just be using it in its problem-solving kind of loop. So you could also try to incorporate this into a more, I guess, automated workflow where, instead of in an interactive environment, you kind of try to build your own kind of script that directly prompt the AI, and then just so Lean-to also provides a kind of a simple feedback loop that just allow the AI to call the tool kind of iteratively, right? So that's another option as well. But does that kind of answers your question? So, and then there's kind of ways to build on top of Lean tool to kind of, you can add in more features as plugins where, so some of these kind of testing, right? So property-based testing tools that kind of I added on top of Lean tool basically allows the AI to just call this tool for run tests, right? So basically, I produce a piece of code, and then I can call this tool to generate test cases and run these tests. So yeah, right now it's I would say it's not production quality software, but it's more kind of research, I guess, kind of prototypes. But yeah, hopefully, yeah, if you want to try it out, I can definitely let me know, and I can help you set it up. Thank you.
Okay, if you are willing to help with setting that up, that would be cool, because I think, like, I know Lean, and I know a lot of things about testing and automated testing, and I know some tool chains, but I have no good idea of what is a unit of testing would here, or like really, like, I have no good idea of how it would look in Cursor, for example. Like what I would even write to prompt it, or which kind of tool to use. So yeah, maybe we can set this up together. I kind of hope to some sort of demo.
This actually may be a good segue to the next question that we have. Like if in the sense that like one critical component of this protocol is the specification. That is, I think, in my understanding, assumed to be, let's say, human written and human reviewed. And so Chris has this question. I'm not sure if you want to read it yourself, Chris. Otherwise, I'll just read it, saying that, like, how do you translate safety specifications to Lean? How do you, are they natural language specifications, like don't kill anyone, don't do a SQL injection attack, and also it seems like you also might need an adversarial generator as part of the training of coding models. That's I understand it to be.
Yeah, I think that's a good question. So I mean, so far, I guess my focus are more on the specification just covers what the code is supposed to do, and in the case of, I guess, Lean, mostly pure functions in Lean, then as basically, there's if the solution satisfies the specification, then it's deemed correct in that kind of so like the two examples I give, right? So kind of if it returns the object that satisfies these exact properties, then it's deemed correct. But I think, yeah, but in general, yeah, especially with a code that has side effects that you, I think we will need to have a formal language that talks about what kind of side effect it has, and so I think this is a kind of there's a lot of research in software verification about kind of reasoning about code with side effects that I'm still learning more about myself. Yeah, my background is more in AI, but I think there's kind of opportunities to bring in kind of more discussion from formal verification, and a lot of times these formal verification tasks looks very hard, but also perhaps with help of AIs, it can help build some of these infrastructure to allow, talking about, kind of these kind of safety aspects of these effects. But yeah, I would say it's a relatively open problem.
Yeah, it is definitely an open problem to have like a formal world model that can be expressed symbolically in not an easy thing. We might have another question here. Do you want to, Manu, do you want to speak it out? Oh, the phone will die, okay. How do you see the bridge between current empirical evidence and more speculative projections about future capabilities of Miller?
Sure.
Well,
yeah, I read the question. I think, yeah, it's an interesting question. Yeah, that's why I was interested in vibe coding as well. I think vibe coding is something, it's meme, but I think it's definitely it gets at kind of a core need by us humanity, right? To say, we want to create this thing and we know what we want, right? So how can I realize the idea? And do I actually need to be a programmer to do that, or can AI help me do that? But for this exact question, that the reasons that I talked about in the talk, right? So one is hallucinations, right, and the other is safety, right? So this vibe coding often doesn't work, right, because there's no check, right, for hallucination, right? So there's no check for safety, right? So and I think that's where, yeah, formal methods can definitely help. But yeah, I think we're kind of a long way away, but I think but I think it's kind of the direction is promising, in that by showing that kind of formal methods can be used to detect hallucinations, that can get more people interested in doing research in that vein, right? So ultimately, I think that is a promising way to scale up, right? So regardless of the safety question, right? If you're able to formally prove that each component is correct, right, and then you will have a better chance of combining these components to create kind of more and more complex software, right, than if you're purely relying on kind of vibe coding puts.
All right. Well, thanks so much, GasStationManager, today for presenting this work, and thank you everyone for attending. We're out of time now, and until next time. Thank you very much.